Another aspect of inferential statistics beyond hypothesis tests and confidence intervals for estimating things or testing hypotheses is to determine whether a relationship exists between two or more quantitative variables. We say a correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between two variables when there's a correlation, and if we plot the pairs of data, like XY pairs, we get an approximately straight line. We'll be looking at correlation in section 10.1. Regression is a statistical method used to describe the nature of the relationship between variables, positive, negative, linear, or nonlinear. And we'll look at regression in section 10.2. First, let's talk about the linear correlation coefficient, which we'll call R. And this is a statistic coming from a sample. R is a number that measures how well paired sample data fit a straight line pattern when we graph them. We use this sample of paired data, sometimes called bivariate data, to find the value of R, and then we use R in a t-test to decide whether there is a linear correlation between the variables. The population correlation coefficient is denoted by the Greek letter rho, and rho is computed by population data. We'll use rho in our hypotheses for a correlation test. The correlation coefficient can range from -1 to 1. If there's a strong positive linear relationship between the variables, the value of R will be close to +1. If there's a strong negative linear relationship, R will be close to -1. We're only looking at linear relationships for our class, essentially meaning that if we graph the numerical data as ordered pairs, we want to determine if they create or if they approximate a straight line pattern. So we'll look at methods for conducting a hypothesis test that can be used to decide whether a linear correlation exists. Some questions that we'll be answering for this chapter. Are two or more variables related? We're going to focus on two variables for now. Higher level classes would look at more variables. If so, how strong is that relationship? Both of these questions are answered by determining the value of R. And then what type of relationship exists? Is it a positive linear relationship, a negative linear relationship? Is there no linear relationship? Or is it possibly something else? We could have correlations that are not linear. We could have quadratic correlations, exponential correlations, and many other functions that we've discussed previously in algebra classes. But again, we're only focusing on linear functions for our class. And a fourth question, what kind of predictions can be made from the relationship? We make predictions all the time. Weather forecasting, stock market analyses, sales predictions, crop predictions, gasoline prices, sports predictions. Some predictions are more accurate than others due to the strength of the relationship. We'll look at a scatter plot of the data. A scatter plot is a graph of the ordered pairs of numbers consisting of the independent variable, which we'll call x, and the dependent variable y. We can use a scatter plot to determine if there is a relationship between two variables. For example, in our picture here, the data seem to follow a line, although they might be a little clumped together. We still have a linear pattern. We say there's a positive linear correlation between x and y, because if we look at the line, it's increasing if we move from left to right. So the slope is positive. We will look at how to calculate the actual equations of these lines in section 10.2. Notice the correlation coefficient is 0.859, and that is close to 1. We could also consider a negative linear correlation here. Notice that r is negative, and it's close to -1 in this case. And we also see that our slope is negative. The slope is not equal to r. R only tells us positive or negative slope. We actually have to calculate the value of the slope using the data. We will actually calculate the value of the slope, which could be any positive number for a positive correlation or any negative number for a negative correlation. 2 more scatter plots. Notice in the first one there's no distinct pattern. It looks like it's just a mess, a cloud of points. And so we say there's no correlation between x and y in this case. And also look that our correlation coefficient is close to 0. And in the fourth picture, there is a distinct pattern suggesting there is a correlation, but that pattern is not linear. Notice that our linear correlation coefficient r is 0.330, which is close to 0. So it's not indicating that there's a linear relationship, but it looks like there is some just from the scatter plot. It's making a pattern. Looks like a parabola. Here I'm going to show you in Excel how to create a scatter plot from some data. The data in this Excel worksheet is not the same as what's in the focus notes. So you could try the focus notes on your own and see if you can match the graph that I've already given you in your notes. But I'll walk you through the same steps. So first up, once we have the data, we want to make a scatter plot. We'll select the data, and then up on the top ribbon, you see Insert. We're going to insert a chart, specifically a scatter plot. And you see a cloud of dots here near the bottom. We're going to click down on that, and we could pick a scatter plot. We could pick one that's connected somehow. We don't want connections right now. Scatter plot just means plot the dots. So we're going to click on that first example. And I'll move my graph over so we can see the graph and the data. And then we need to do some checks, making sure that our data was plotted correctly. We have a 6 and a 4 and a 6 and a 10, and it looks like those are those 2 points, 2 and 18. So it seems that our data was plotted correctly, 10, 33. So the x, the hours, the x is the x-axis, and the amount, y, would be the y-axis. And so when we're plotting 6, 4, we would find 6 on the x-axis and 4 on the y. Okay, now we cannot leave that scatter plot like that. That's not cool. We need to come in and make some changes. Give it a title. We're talking about sleep and drinking milk, so sleep and milk consumption sounds good. And then we need to change the axes. We need to label the x and y axes. If you're on a PC, when you click on the chart inside whitespace, you get 3 options to pop up, and you can click on that plus to add a chart element. Showing you here, you can see you can click on axis titles and it shows up on the x and the y axis. This is one way to add the axis titles. But if you're on a Mac, under the chart tool ribbon, you should be able to see something called add chart element. So Macs don't have this option, I believe, but they do have the add chart element option. So if we click here, then we can add a primary horizontal, and we have to repeat it, a primary vertical. And if we double click in here, highlight the words, we can label our axes. It is really important that you label your axes. You need to be able to show someone else your graph, and that person should be able to read that graph without having to ask you, what is x? What is y? What am I looking at? And you want to make sure you include units. The x-axis is in hours, the y-axis is in ounces, so those are labeled. Now, looking at this scatter plot, does it seem that a linear correlation exists? Does a linear relationship exist between the amount of hours people sleep and the amount of milk they drink? Not really. It kind of seems like a cloud of points. Let's take a look at another example. On number 2, the average gasoline price per gallon in cities and the cost of a barrel of oil are shown for a random selection of weeks in 2015. Is there a linear relationship between the variables? We'll construct a scatter plot. So we'll grab the data, click on Insert, find that scatter plot. We'll give it a title. We'll add some axes, titles. And looking at this, it seems that there is not a linear relationship. It almost looks like a sideways parabola. So we would say again, no linear relationship for the oil and gas prices. Now, the formula for the correlation coefficient is given here. And we see that summation notation happen again. But we're not going to use this. It takes a really long time to calculate it by hand. There are chances for mistakes. So we're going to use the power of Excel. And so we have an Excel formula, Correl, array 1, array 2. So I'm going to calculate that right underneath. We'll say equals Correl, and then we're going to select the data for the first variable, comma, select the data for the second variable. Hit enter. And this value, 0.15779, this is our linear correlation coefficient for the oil and gas price data. So rounded to 3 decimal places, we'll say 0.158. R is too close to 0, so it definitely shows there's not a linear relationship. Some properties of the linear correlation coefficient. R is always between -1 and 1, including them. If all values of either variable are converted to a different scale. If we multiply all of the oil prices by 20, for example, the value of R does not change. R is not affected by which variable is considered X versus which is considered Y. If we were to switch the X and Y values, R doesn't change. And R measures the strength only of a linear relationship. Any other relationship, and we cannot use R. We have to use something else. There is a t-test for the correlation coefficient. A t-test for a linear correlation. We're going to make that change right now. And that test statistic is right here. T equals R times the square root of n minus 2 divided by 1 minus r squared. We have r and n that we're using. So once we have the value of r using Correl, we can plug that in along with our n and find our test statistic. We can go through the same comparisons that we did for t-tests in chapters 8 and 9. Correlation tests are always two-tailed. So our critical value will be plus or minus t inverse of 1 minus alpha over 2 with degrees of freedom equal to n minus 2. Notice this is the first time our degrees of freedom is not n minus 1, it's n minus 2. And n is the number of pairs of data. So if we go back to our oil and gas prices, there are 6 pairs of data, 12 total numbers, but since they are paired, we would say 6 pairs of data. If we were running a hypothesis test for the oil and gas prices, our degrees of freedom for that t-test would be 6 minus 2, which would be 4. We've got some requirements before we can do a linear correlation test. We can always compute the linear correlation R, but if we want to make a conclusion about a linear correlation, a statistical conclusion using a hypothesis test, we have to make sure that we have these 3 requirements. The sample of paired data is a simple random sample of quantitative data. In most cases, we'll already have that. The scatter plot must confirm an approximate straight line pattern. And if there are outliers, if there's 1 or 2 points that are far, far away from the complete rest of the data, we may need to throw those outliers out. So 2 and 3 are just simplified attempts at checking a formal requirement that the pairs of data have what's called a bivariate normal distribution. They're normally distributed, but in this bivariate 2-variable way. In order to conduct a formal hypothesis test to determine if there's a significant linear correlation between 2 variables, we'll have the following null and alternative hypotheses. The null hypothesis, rho equals 0, there's no correlation. And the alternative hypothesis, rho is not equal to 0, there is a correlation. So the null hypothesis means there's no correlation. If we do not reject the null, there is no significant linear correlation between the variables. The alternative hypothesis means that there is a significant relation between the variables. If we reject the null, then that means our alternative hypothesis holds. We would have evidence to support a conclusion of linear correlation if we reject the null. So if we want to show a linear correlation, we want to reject the null hypothesis. Possible relationships between variables. When the null hypothesis has been rejected, that means there is a significant correlation between variables. Any of the 5 following possibilities can exist. There could be a direct cause and effect relationship between the variables. X causes Y. Water causes plants to grow. Heat causes ice to melt. There could be a reverse cause and effect relationship between the variables. So there could be the case that Y causes X. An example, suppose a researcher believes excessive coffee consumption causes nervousness, but the researcher fails to consider that the reverse situation may occur. It may be that an extremely nervous person craves coffee to calm his or her nerves. It's a possibility. It could be the case that the relationship between the variables is caused by a third variable. Here we have plots of ice cream sold and shark attacks, and it looks like they're pretty closely related. But we know that eating ice cream does not cause shark attacks. So that third variable is just the fact that we increase ice cream and shark attacks in the summer. We eat more ice cream because it's hotter, and we go in the water at the beach because it's hotter and the beach is usually cool, and we can play, and there could be sharks. There may be a complexity of interrelationships among many variables. So just because we're analyzing 2 variables doesn't mean that those are the only 2. We talked about confounding variables before, way back in chapter 1. There could be a situation where we have confounding variables that are causing other changes to happen than just X causing Y. So some common errors involving correlation. Often people confuse correlation with causality. So what I mean by that is like the first two possible relationships between the variables. X causes Y or Y causes X. If we can show linear correlation, that does not mean at all that X caused Y or Y caused X. It only means that as one variable goes up, so does the other one. Or as one variable goes up, the other one goes down in a linear pattern. In order to show causality, we would need to conduct experiments. Using data based on averages, we never want to use averages as the data when we're trying to conduct any test. If we're only looking at averages, we don't know what the number of variables that were added together and divided by. So we could have one set that had 10 data values, and we could have another set that has 300. But if we're only using the averages from those two data sets to somehow come up with a test, the smaller of the two sets gets weighed equally to the larger ones, and that's not very accurate. Another error involving correlation is ignoring the possibility of a nonlinear relationship. When we're doing linear correlation, we're always going to be using the two-tailed test. But it could be the case that we can look at only one tail and we can form an alternative hypothesis that's strictly less than or strictly greater than. So for us, I just want you to know that can be done, but we will always be using a two-tailed test. We'll always be using a two-tailed test for our test for linear correlation. Next up, we'll do a few examples of these hypothesis tests for linear correlation.